So, hello everyone. Welcome back to ESEM 20, now with the session on testing, reliability and security. In this session, we actually have 3 presentations. 2 of the 3 accepted industry papers will be part of this session. And we now start with the first industry paper presented by Runeson, which is about getting started with chaos engineering, design of an implementation framework in practice.
Thank you very much, Michael, and hello everybody. This is an industry track paper, as mentioned, and the main work is conducted by my master students, Hugo Jernberg, and advised by myself, Runeson, and my colleague, Emelie Engstrom. The industry context in which we conducted this work is ICA-gruppen, the ICA Group. It's a series of grocery retail operating in Sweden and the Baltic countries. In addition to the grocery business, they have a real estate firm, a chain of pharmacies, and a bank. Turnover of the group is around 120 billion Swedish krona. The ICA Group, they combine private store ownership with central scale and opportunities. So the individual stores are owned by local dealers, but the group corporation, they support with financing, they support with concept development, and in this context, first and foremost, they support with digitalization. So the problem we address in this project is related to that the IT systems are developed and operated by ICA Group, the central corporation, and then offered as a service for the individual retailers. And they can, to some extent, do local tailoring for the web presence, for the advertising, so they can advertise locally what they want for their local markets. And they also offer e-commerce services through this platform. The IT department of ICA-gruppen is distributed over several segments of the company, and they have hundreds of employees. These IT systems are business critical for the ICA-gruppen as such, and also for hundreds of retailers around Sweden and the Baltic countries. So it's ultimately critical for them to have good service and reliability. The problem we wanted to analyze in this project was how to validate and improve the resilience of these large-scale business-critical software systems. And they had an idea of implementing chaos engineering to help in this validation. And that's where this project started. It was initiated by and carried out by the centralized IT department, but it was also aimed to be a lighthouse project where in this distributed IT organization, they could pick up and implement the chaos engineering practices in different places. And we also aimed the descriptions, as we published in the papers, to be generalized for others who want to get started with chaos engineering. So what is then chaos engineering? It's defined as the discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. So it's kind of stress testing, but it's primarily intended to verify that features that are intended to create this stability actually withstand the hypothetical turbulent conditions. The practice is originally developed at Netflix, and they have published several books and papers on how they implement it at Netflix. The basic steps of chaos experiments is to start defining a steady state, which is the normal behavior of the system under test. Second, hypothesizing an effect of an chaos experiment, which then stresses the systems in one way or another. Thirdly, run experiments on the real-world system by creating some kind of disturbance on the system, and then following up and measuring whether or not the system could withstand this kind of stress or not. Our main goal in this project was to see how to take the experience and the knowledge from Netflix and others who had applied chaos engineering and implement into ICA-gruppen. The main contribution is the chaos engineering framework, which consists of 4 recommended activities. Each of them split into several steps. In the paper, there is a short version of the guides for each of the steps, and there are also 3 defined outputs, which we refer to as documents, but they could be implemented as databases or specific tools. The first activity, the discovery activity, defines the system under test, which type of system we are talking about. There is a taxonomy in the framework, and that taxonomy also helps choosing which tools to run for this specific type of system. For experiments that we think will be well handled by the systems, remember that we are experimenting with operational systems. We add them to the backlog of experiments. So that's a list of experiments we would like to perform. If we expect the system not be able to handle the challenge, we create an improvement opportunity. So a list of improvements to be made to the system to withstand this stress. So, and this improvement opportunity could be either to improve the monitoring of the system so we can see better what's going on, or to improve the resilience mechanism of the system in itself. So this is the discovery phase where we come up with the experiments to be conducted. Next is the implementation phase, where we select the top priority chaos experiments and then we define the monitoring metrics, which tools to use, we configure the experiments, we run the experiment and evaluate the outcome. This implementation can keep going, and we run the next experiment and the next experiment. However, from an organizational point of view, chaos engineering can be advanced by entering the sophistication phase. The sophistication phase involves an analysis of how mature the whole organization is in their application of chaos engineering. And this assessment results in a sophistication map, which is kind of a maturity model of the organization. Based on this map, strategic decisions can be made on where to expand the experimentation based on the importance and state of practice. This may involve extended use of features in the existing tools or introduction of new tools. So in this way, there is this inner cycle where we select new experiments from the backlog and run them, and the outer cycle where we take a look at the status of the chaos experimentation overall. You can read a lot of more details in the paper about this, and there is even a more comprehensive master thesis report with even more details. How did we come up with this framework? The research methodology is the research is conducted within the design science methodology framework, and the problem was conceptualized by studying the literature. There are 6 peer-reviewed papers and 6 industry experience reports, which constitute the basis for the work. We also conducted interviews with people in the IT organization and people experiencing incidents in the organization. Then we devised the solution. We further interviewed people in the ICA group and organization about areas which may be important for chaos engineering. We surveyed openly available tools, 27 tools in total, which are listed in the paper. And we also demonstrated proposed solutions and evaluated it with a questionnaire with people. Finally, we validated the framework. Unfortunately, we did not have time to make a full validation, but the first 1.5 steps were validated on 2 teams and systems. So we could see what kind of tools that were useful and which type of experiments that came out from this process. So in summary, we recommend companies using this framework as a guide for implementation of chaos engineering, and we hope that will help them. The framework is rooted in real-world problems in a real corporation. It's based on all existing literature and the available tools. And it's implemented in practice, and I can tell that I'm still a customer of grocery stores of this ICA group. So this far, it seems to work.
Yeah, Beth, many thanks for the great presentation. I'm also bought things at ICA several times in Sweden, so everything works well. Okay, so still there is the chance to ask questions via the chat, maybe in Facebook or in YouTube. Both is an option. So for now, I have one question. So to what extent have you tailored the approach that Netflix came up with and proposed?
So one core thing is this in relation to the distributed organization, and we needed a kind of very basic but still standardized way of working. So terminology, these 3 different outputs, so they could within the organization, when they talk about chaos engineering, they understood each other. And also we based all work on the available open source tools and the specific types of systems and techniques so they had within the company. The pairing between tools and techniques is needed. And also from a practical perspective, we guided this from a starter to select, so they utilized the features from fewer tools rather than adding many more tools. Okay. But it's very much a synthesis of existing experience from Netflix and others who have applied it.
Okay, thanks. So there are 2 more questions that came up. So one is, can you provide us lessons learned, preliminary results from your 2 evaluation studies?
Yes, actually, it's quite interesting to see that the outcome is different from these two. From one of them, so the set of experiments that came up was quite different in the two different applications. So it shows us that even though within the same organization, we can come up there might be some areas in more need of testing or improving the resilience mechanism compared to others. So that's what we can see by applying to these two different systems and teams. Then, of course, we would need to follow up with a broader evaluation to see more variance of the output.
Okay, thanks. And just one last, please, short answer. Which evaluation steps you did not have time to complete, and how relevant you think they are compared with the ones you did?
So what we didn't have time to complete is this long-term strategic work with chaos engineering. So we didn't. That would, I mean, I would like to come back after a year and see how they actually worked with this and whether it helps and which of the tools were helpful, etc. So we applied the first steps to get started, but I would like to follow up on a longer perspective to see what it really means in practice.
Okay, many thanks. Okay, so now we come to the second presentation in this session on testing security and reliability, which is given by Gregory Gay on understanding the impact of solver choice in model-based test generation.
Perfect, thank you. This is a relatively short slot, so I'm going to dive into the talk. I would definitely recommend, if you're interested, please read the paper and check out our data set, and I will provide links to those at the end. Anyway, a common form of model-based test generation is based on the use of bounded model checking, where properties that we expect from the model are embedded as Boolean predicates describing the states we encounter during particular execution paths. So model checking relies on the use of an SMT solver. These solvers explore the state space of the model, looking for states that violate those properties by casting property violations as a Boolean satisfiability problem. So what we do here, we seek values for the input variables of the model that lead to a state violating those properties. If the model checker can find that, it produces a counterexample, a partial test specification that demonstrates that violation. So often what we do is we take properties we want to show can be met, we negate those saying, oh, look, no, you can't actually meet those. And then the model checker is going to attempt to produce a counterexample illustrating how the property can actually be met. This counterexample offers us test input that can be applied to a real system or to the model itself to help demonstrate that it can show, in fact, a property of interest. Now, many different SMT solvers exist that can power this exact process. And once upon a time, you might not have had a choice of solver. Each follows their own algorithm, each may produce different counterexamples, each may be suited to particular classes of problems or types of models. But now, this choice is less clear. With advances in computing power and algorithm design, we increasingly encounter these situations where multiple solvers can produce test cases for a particular model. And in that situation, it doesn't matter which solver you use. And that's what we wanted to know in this experiment. So to look into this, to look into whether solver choice matters in terms of fault detection, and to look at the factors that might influence that result, we put together an experiment where we gathered a set of case examples, a set of 37 different models written in a language called Loost. These solvers contain various data types of Boolean and numeric data types, as well as enumerated types. And for each of those models, we generated a set of faults. So we seeded up to 500 mutations, faulty versions of each model, each of those faulty versions containing a single fault. For the original models, we generated test suites. We used 4 different solvers, each using different algorithms and supporting different underlying theories. Z3 from Microsoft, MathSat5, CVC4, and Yikes2. Now, all 4 of these should work for our set of 37 models, allowing us to compare the resulting test cases and how effective they are in a fair manner. Now, when we generate tests, different sources of testing goals may impose different constraints on the produced test suites. So in this study, we focused on testing based on structural coverage criteria, and we used 4 different ones: branch, condition, decision, and MCDC coverage, in order of complexity and difficulty of satisfaction, from simple branch coverage to more complex MCDC coverage. All of these, though, center around different ways of executing Boolean statements in the models. And we computed the effectiveness. So we looked at the number of testing goals satisfied by the test suites. Could we fully satisfy the set of testing goals for each solver? And we looked at the fault finding effectiveness on those seeded faults by each test suite. To judge the correctness of the system behavior, to judge fault finding, we need a test oracle. And the oracle specifies expected values for a set of variables. So we can vary the size of that set. Specifying expected results for a varying number of variables from the program. Right? We vary the size of that set, as one solver may be better at propagating the faulty state to a monitored variable than others. And so we use 2 oracles here: a standard oracle based on the output variables alone. This is more what you'd use in practice, as well as a maximally powerful oracle that checks the program behavior for every single variable, internal and output, in the model. So what did we find out? Well, our first research question looked at the solvers in terms of their ability to generate test cases. Are there models where certain solvers cannot satisfy all of our solvable testing goals? What we saw was that Z3 and Yikes2 did achieve full satisfaction over the entire set of 37 models, while CVC4 and MathSat5 fell short for 7 of those models, not giving us full results. Now, some of those were 90-something%. Others, though, they were only able to satisfy a small subset of the testing goals. Now, in this experiment, we provided all of our solvers with the same timeout, either 72,000 seconds per testing goal, or a path with a length of over 500 state transitions. Both of those limits are well over what's generally required. Generally, this was a matter of a few seconds and maybe 5 transitions. So timeout in these cases doesn't necessarily imply that they would give us a test case with larger timeout. More likely that these solvers would never be able to satisfy those goals. So we do see that not all the solvers are equally effective on these 37 models, but most of them, on 30 of those 37, all 4 solvers can give us test cases. Now, how effective are those test cases? Right, our remaining research questions look at the impact of solver choice on fault detection capabilities of the generated test suites. And so there are 18 models of the 37, and of the 30 that we could achieve full satisfaction of. Right, so 18 of the 30 fully satisfied models where performance differs between the solvers across all 4 of the coverage criteria. So essentially, what we saw, in short, was that there was a difference. That for the output-only oracle, checking the output variables of the model, your common oracle, CVC4 and MathSat5 outperformed Z3 with significance. When we extended this to the maximally powerful oracle, CVC4 and MathSat5 outperformed Z3 and Yikes2 with significance. Right, so these are the 2 solvers that couldn't satisfy every single model, but for the models they can satisfy, they attain better performance than the other solvers. Now, why is that? Well, our goal in this experiment was not necessarily to recommend one single solver. Really, what we want here is to make recommendations for solver improvement across the board. So we've examined the impact here of a number of factors, and the first of those is the test oracle you employ. Right, so in this experiment, we used 2 different oracle formulations. The output-only oracle is the standard practice. We're going to specify the expected values for the output variables of the model. The maximum oracle reflects a situation where we specify expected values for every single model variable, internal or output. And that's not a realistic oracle, but it is really useful for looking at our best case performance. The maximum oracle is useful for understanding a critical feature of solver performance, which is the ability of the solver to choose input that both triggers faults and propagates the expected or propagates the effect of that fault to the output where we can see the effect. And there's a clear performance gap between the two oracle types, which indicates that some faults are triggered, but the corrupted state is not propagated to the output level. So rather than suggesting a difference between the four solvers here, this identifies an area of improvement for future solvers and test generators. Solvers and test generation frameworks could improve fault detection by factoring propagation and likelihood of propagation into the input selection, using path constraints to ensure path between variable assignment and observation through the output. And we can factor this into the constraints being solved, making constraints harder to solve, but potentially ensuring higher likelihood of fault detection. Now, all four sources of testing goals we used in the study are structural coverage criteria based on Boolean expressions. Coverage criteria does influence the resulting fault detection. The MCDC satisfying suites detect more faults than those that satisfy the weaker criteria like decision or branch coverage. But that rise occurs regardless of the chosen solver. However, what we did see here that is related to solver performance from the results of MCDC is that there is a relationship between the solver and how it searches for answers and the source of testing goals. So for branch, condition, and decision coverage, there are clear performance differences between the solvers. Some are better than others. For MCDC, the performance is actually quite similar. This is interesting because MCDC is the strictest of the criteria. It imposes the most constraints on the input you use to satisfy its goals, and so it follows that the solver would have less freedom to choose input that meets the goals of MCDC, narrowing that performance gap. Simple goals can be satisfied by a wide range of input. More difficult goals require a smaller selection and are more difficult to solve. And so the choice of testing goal is up to the developer, up to the tester. But as these solvers increase in their efficiency and their ability to solve complex constraints, the advice to the developer then would be to use these stronger criteria like MCDC, in turn making the choice of solver matter a bit less. Now, like in standard programs, model variables have data types, Boolean, integers, etc. How those data types are handled differs greatly between solvers, and a lot of the performance gap we saw came down to how the solvers chose the variable values. And the models where the test suites differ the most in performance were those with numeric input. What we saw was that CVC4 and MathStat5 chose a far wider range of values for numeric variables, a much more dynamic search strategy than was used by Z3 or Yikes2. So by applying a wider range of values, the test suite was more likely to stumble on those particular inputs that exposed the fault. We observed a similar phenomenon for Boolean variables at rare times, where Z3 would be the top performer. And what we saw was that Z3 also tended to set Boolean variables to true values more often than the other solvers, which tended far more toward false values. So the effect is more muted than with numeric variables, as there's only two options really. But again, by trying a wider range of values, Z3 generated better test suites in that situation. And so solvers could improve fault detection by applying a wider variety of values to variables rather than tending more toward fixed values. Likewise, the counterexamples being produced by the solvers are a partial test specification. Solvers will only provide values in a counterexample for input variables that directly impact the execution path, leaving others omitted. Now, that's a deliberate design decision. Solvers can simplify the state space by dropping these unnecessary variables. Now, if a value is not provided in the counterexample, the test generation framework needs to fill in something to create the concrete test case so that it can apply to the real system or the model later on. This will often be a default value like 0 or false, and as we saw, constantly using the same values tends to decrease the probability of exposing faults. And so the strategy used by the test generation framework to fill those gaps is also going to impact fault detection. The test generation framework could, for example, apply random values instead of a static default, and that might boost slightly the odds of fault detection. Now, the last element here is parameter tuning. So to avoid bias in our experiments, we used the same settings regardless of the solver being employed, However, every solver offers a number, maybe even dozens of parameters that you can use to tune the search process. As has been seen time and time again, general solutions can be outperformed by tuning a solution to a problem. And so by tuning the parameters used by the solver to control its search strategy, we also are likely to see further improvements in performance. Automated approaches to parameter tuning have been proposed in multiple domains, usually using some form of reinforcement learning. And this is another situation where we may want to work on better processes to automatically tune test generation frameworks and their underlying solvers automatically. So the results of our experiments did show that the solvers varied quite a bit in their ability to produce counterexamples and in the resulting fault detection of the generated test suites. The choice of solver has an impact on the test suite, regardless of the oracle, model structure, or source of testing goals. Now, I know this was a short talk and I blew through it quickly, so I'd be happy to answer your questions. I would also recommend checking out the paper and our data set. But yeah, like I said, I'd welcome any questions.
Many thanks, Greg, for this great talk. So still there is the chance to post a question. So I have at least one. Can you, does the modeling language that you actually adopted have an influence? And can you summarize the mutations that you performed?
Sure. I do not know, honestly, if the modeling language has a particular impact. I would suspect not. I think it's going to come down more to the search strategy used by the solvers. The language we used, Loost, is not incredibly common, but what it is kind of an intermediate language that translates well. So most of these were originally state flow models that were translated to Loost and can be then translated directly into C as well. Then we got some of these are open source, others are from industrial partners. But I don't think the modeling language is going to have a huge impact. I think it is going to come down more to the general strategy of the solver. In terms of mutations, there is a list of them in the paper, but these are mostly fairly typical. Things like swapping out your less than for greater than, swapping out your arithmetic and Boolean operators. There's some order swapping of statements. The Loost language has a delay operator where it can use a value of a variable from a previous round of execution, and sometimes will insert or delete those as part of mutations. But there's a full list in the paper, and I am drawing a blank on the other ones at this moment.
Okay, yeah, thanks. There is one last question, which is there any tool that combines the results from multiple solvers?
I'm not aware of anything at the moment, but you could always run multiple solvers and compare or add to the results. The ideal case would be that you can somehow automatically tune these to get just the best possible performance with just starting with one from the beginning. But I could see potential opportunities in the future for combining results of different solvers, and I think that'd be really interesting to look at.
Mm-hmm. Okay, many thanks again.
Thank you.
And now we come to the third talk in this session, which is about what makes Agile test artifacts useful, an activity-based quality model from a practitioner's perspective, given by Jannik Fischbach.
Yeah, hello. Can you see my screen? Does it work? Yeah? Or not? Okay, hopefully. Okay, yeah, then thank you for the introduction. This is a paper written by me, Henning, Daniel, Davide, and Andreas. And since this is my first presentation here at the empirical software community, I just want to use the opportunity to introduce myself just shortly. I'm a PhD candidate at the University of Cologne, and I'm mainly dealing with agile testing, and especially how you could use natural language processing techniques to help practitioners in agile testing and also requirements engineering. And so far, I wrote 4 different publications. Today, I will present here the third one, so feel free to have a look at the other papers, the preprints and proceedings. Yeah, so today I want to talk about agile software development and especially the testing part of it. So I think we agree that the Agile Manifesto is the theoretical foundation for Agile software development, and it promotes 4 different principles. And today I want to talk about the second principle. So working software over comprehensive documentation. And the Agile Manifesto promotes that Agile practitioners, they only need few artifacts to convey information. Instead, they should focus on working software. So you don't need to write down any comprehensive documentation, and you don't need so many artifacts. And driven by this principle, there are some frameworks such as Scrum or SAFe framework and so on. And they mention also only a few artifacts that should be created and used and maintained by practitioners. But some of our research colleagues, they have already shown that Agile practitioners increasingly disagree with this principle. So they need other artifacts which are not introduced by these frameworks for different reasons. So they need additional artifacts for team governance or for internal communication, external parties. And the fourth point, this is the reason I want to talk about today. These additional artifacts are used for quality assurance. So here we talk about test artifacts, which are used by practitioners to test their software. Yeah, and based on these studies, we know which artifacts are used by Agile teams, or also all these additional artifacts which are introduced by the teams on their own initiative. And we also know why they are needed. But we still do not know how these test artifacts are designed in practice if we think about some Agile development projects. And more importantly, we also do not know which properties make these test artifacts useful for the practitioners to test their software. So there are already some normative standards, for example, the acceptance testing side or some ISO standards. But there are some problems with these standards because they only describe the properties for the artifacts which are introduced or mentioned by these traditional frameworks. So the list is not complete because they do not cover these additional artifacts. Also, these normative standards describe the quality by using some really abstract properties. So, for example, one property would be that acceptance criteria should be both precise and concise, but we do not know explicitly what means precise or what means concise. And the third point is that the empirical basis is missing. Yeah, and we tried in our paper to address this research gap, and we follow the idea of activity-based artifact quality models. So let's talk about these quality models. So basically, these quality models are based on the idea that the quality of an artifact depends on the stakeholder who uses the artifact, and also the activities, so the context in which the artifact is used. And here below, you can see the meta model of such an activity-based artifact model. So basically, you have, for example, an activity which is performed by a certain stakeholder. You also have some artifacts. Of course, some artifacts can extend a super artifact, and these artifacts, they have a property, and we call these properties a quality factor. And this quality factor has either a positive or negative impact on an activity. And if this quality factor has a positive impact, then of course it has a high quality because it's useful for the practitioner, and it helps the practitioner during its carrying out a certain activity. But if there is a negative impact, of course, you should avoid these quality factors. And in our paper, we created such an activity-based quality model, and to understand which quality factor has good or negative impact on a certain activity, we first studied current challenges. So we talked to stakeholders and asked them, okay, how do you use the artifacts? How do you design them? And which are the challenges you are facing? And after that, based on these challenges, we derived the quality factors to understand which factors are good and which are bad. So in a nutshell, we had an interview study with 18 different stakeholders from different domains. And of course, at the beginning, based on the quality and use paradigm, we created the questionnaire, and we validated the questionnaire, and also recorded all the interviews and had a validation process with them students. So basically, in the beginning, we took the recordings, derived the quality factors and the challenges, and then we double-checked the quality factors. And in the end, we came up with the big activity-based quality model. So of course, in these short time slot, I cannot talk about all quality factors and all challenges. I just want to give you a short introduction and a short overview. So on the left side, you see some of these challenges which we identified in our study. In total, we identified 9 different challenges, and today I want to talk about the top 3 in the last remaining minutes. Yeah, and based on these challenges, because if you talk to stakeholders, and the stakeholders, for example, explains, okay, acceptance criteria ambiguously formulated, so this is the top 1 challenge, then you need to go one step further and ask them, okay, what do you mean by ambiguously? How should acceptance criteria be formulated instead to be useful for you in your activities? And we did that based on these challenges. And in the end, we came up with 16 different quality factors for 6 test artifacts. And on the right side, you see our final activity-based quality model. So the gray boxes are the quality factors. Of course, we have the stakeholders with this man icon and also the activities. But I think if you have a look at the paper, it becomes even more clearer. Okay, so then let's talk about these 3 top challenges. So the first challenge, of course, was acceptance criteria are ambiguously formulated. So a lot of practitioners, they told us, okay, I'm a test designer and I want to derive the right test cases from my acceptance criteria, but I do not know what the system is supposed to do. And based on this ambiguously formulation, we do not know how to derive the test cases and how to test our software. And that's also a big challenge in agile software development, because due to the high development speed, they are not able to check the formulations of the acceptance criteria, and based and are really dependent on the formulation skills of the business analysis. So here in this challenge, I think it becomes clear that we need an automatic checking for formulations of acceptance criteria. I think this is also a challenge which we saw from traditional projects regarding typical requirements. Acceptance criteria are now the requirements in the agile software development. So and based on these challenges, we derive the quality factors. And below you can see in the yellow box some of these quality factors. So then I asked them, okay, what do you mean by ambiguously? And one quality factor was, for example, vague phrases. So if you use vague phrases in your acceptance criteria, for example, if you write down the system functionality like the system should be able to store your customer data and upload it quickly. So what means quickly? This is vague. You do not know what exactly the system should do. They have also problems with co-references. So if we think about user story in the agile software development process, then usually a user story has more than one acceptance criteria. So they are linked to each other. And if you have co-references in these acceptance criteria, you do not know explicitly which entity is mentioned by one acceptance criteria. So it's hard to understand the relationship between them. And that's why we link here these quality factors with a negative impact for the activity acceptance test design. And for all the other quality factors, just have a look at the paper, then it becomes clear. So we always link our quotes to each of these quality factors, and then I think it becomes clear what we mean by the quality factors. So then this is the challenge. I think this is for me, it's the most interesting part of the paper, because we talked to customers, but also to product owners, and product owners are responsible for the internal testing. So they are responsible for, we call it acceptance testing. So they use these acceptance tests during acceptance testing and check whether the system conforms with user stories and acceptance criteria. And one of the biggest challenge for agile practitioners is to derive the right amount of test cases, because acceptance criteria are usually formulated by unrestricted natural language, yeah, then it's even harder for them, especially if you think about really complex acceptance criteria, to find the right amount of test cases. And then I think if we have a look on the quotes, then some practitioners said, okay, I overlooked some cases, or maybe test designers, they tend only to test the positive case and not the negative ones, and that was a big problem at one, I think it was three different companies, which leads to system defects which are not detected because you do not test the negative cases. Yeah, and based on these challenges, we derived 3 different quality factors, and they are important because they have a positive impact on acceptance testing. So, of course, acceptance tests should be minimal, so they should only include these test cases which are needed, not more, not less. Of course, they should be automated due to the high development speed, and as positive and negative scenarios. And here we should find ways to help practitioners to derive the right amount of acceptance test cases, and especially the negative scenarios. Yeah, the third challenge was about test data. And yeah, it was in our study, it's one of the top 3 challenges. And this is also a challenge which we see in a lot of traditional projects. So even if we change from traditional programming to agile programming, there is still problems, for example, with test data, because there's not enough test data, or even it's even poor test data, because I talked to some developers, and then they told me, okay, yeah, we just use some random values, or we use some values which we know from experience that we need to test them, but there is not, yeah, there's no systematic way of deriving the right amount of test data from production data. So this is basically one of the other challenges. So as you can see on the right side, there are more quality factors, and I think it's better if you read the paper to understand the other quality factors, and especially to find to understand the impact of these quality factors on these certain activities. But overall, we want to give this artifact model to the community so that you can use it for quality control. And it's also I published this model also with the practitioners which we interviewed, so it can be used to understand how you should design your test artifacts, and especially these additional artifacts which are not introduced by the standard frameworks. Yeah, so feel free to have a look at the paper and use the quality model. Thank you.
Yeah, thank you, Jannik, for the presentation. So we are already running out of time. So just one short question. Did you investigate the influence of different types of testing, so in terms of security and performance testing, or did you focus on functional testing?
Yeah, we focused on functional and system testing. So it's because acceptance criteria, for example, they're on the system level. So it's more about system level, not performance testing or something like that. But it would be interesting to investigate it from the viewpoint of this perspectives.
Okay, so questions just came up. You presented an activity-based quality model from a practitioner's perspective. Sorry if I didn't see it. Did you use the model for real projects, and how many projects?
Yeah, so we mean by from a practitioner's perspective because we derive the quality factors from the perspective of the practitioners. Yeah, and it were 18 different stakeholders from different domains, and we merged all these knowledge together and merged it together in one big activity-based quality model. But I can show you again if you want to, or have a look.
I think we ran out of time, sorry. Just the last question. What was the acceptance of the practitioners? Yeah,
at the beginning was quite interesting because we at the beginning we asked them what would be a quality factor which is which constitutes good quality for you. Then it was hard for them, and if then in the end we changed our question strategy and asked them what is a challenge, and it was, of course, some of them said, okay, but please, this should be confidential. And of course we cannot share the recordings, but we can share all the quotes and whatnot. So It's a topic I think some people do not want to talk about, because we start with a negative asking because we ask for challenges and then we derive the quality factors. It's other if it's
Yeah, thank you, Jannik, for the great presentation, for the great answers. So we are now at the end of this session on testing security and reliability, but the next session is also about the topic testing security and reliability, and it starts at 1/4 the full hour, so in more or less 5 minutes. Thank you very much, and thanks to all presenters, the technical support, and the audience.